Here is a question that ought to keep you up at night. When light leaves a star that is 1 billion light years away, it travels for 1 billion years to reach your eye. 1 billion years! That is longer than complex life has existed on Earth. And yet, here's the funny thing. From the light's own point of view, if we can even say such a thing, no time has passed at all. Not 1 second. Not 1 billionth of a second. Nothing. Zero. The journey that takes 1 billion years for us takes no time whatsoever for the light itself. How can that be? How can something travel for 1 billion years and yet experience no time? By the end of this lecture, you will understand exactly why this happens. And I do not mean you will just nod along. I mean you will really get it in your bones. You will see that this is not some mystical poetry about light. It is a direct, unavoidable consequence of how space and time actually work. And once you see it, you cannot unsee it. Now, let us start with something simple. Let us start with time itself. What is time? You might say it is what clocks measure. Fair enough. But what do clocks really do? A clock is just some regular process that repeats. A pendulum swings back and forth. A quartz crystal vibrates. A cesium atom oscillates between two energy states. We count the repetitions and call that time. So time, for any given object, is really about the processes happening inside that object. If you have a little clock in your pocket, time for you is defined by what that clock does. And if the clock stops, well, time stops for you, at least in any meaningful sense. Now, here is a strange fact. Suppose you and I each have identical clocks. Beautiful, precise clocks. We stand next to each other, and our clocks tick together. 1 second for you, 1 second for me. Perfect agreement. But now suppose you get on a rocket ship and fly away from me very fast. What happens to your clock? You might say, well, nothing happens to my clock. It is the same clock it always was. It ticks at the same rate it always did. And from your point of view, that is absolutely true. Your clock keeps perfect time. You feel nothing strange. 1 second follows another, just as it always has. But here is the strange part. From my point of view, watching you zoom away, your clock is running slow. Not because it is broken, not because there is anything wrong with it, but because of the nature of space and time themselves. Your clock actually ticks slower relative to mine. And here is the thing. This is not an illusion. This is not some trick of perspective. This is real. If you fly away very fast and then come back, we can compare clocks. And yours will have ticked fewer times than mine. Less time will have passed for you. This has been tested many times with atomic clocks on airplanes. It is a fact about nature. So time is not absolute. Time depends on how you are moving. The faster you move relative to me, the slower your time runs relative to mine. This is called time dilation. Now, you might ask, why? Why should motion affect time? What is the connection between moving through space and the rate at which time passes? This is where Einstein comes in. And it starts with a very simple observation about light. You see, light is strange. It does not behave like other things. If I throw a ball at 10 miles per hour while I am standing still, and then I get on a train moving at 50 miles per hour and throw the same ball, the ball goes faster relative to the ground. That makes sense. Speeds add up. But light does not work that way. If I shine a flashlight while standing still, the light goes at the speed of light. We call that c, about 186,000 miles per second, or 300,000 kilometers per second. Very fast. Now, if I get on a rocket ship going half the speed of light and shine the same flashlight forward, you might expect the light to go at 1.5 times c. After all, my speed plus the light's speed, but it does not. The light still goes exactly at c. Not faster, not slower, exactly c. This was discovered experimentally, and it was very confusing. How can that be? How can light always go at the same speed, no matter how fast the source is moving? Einstein realized that the only way this can make sense is if space and time themselves are different from what we thought. If the speed of light is truly constant for all observers, then something else has to give. And what gives is our notion of absolute time. You see, we naturally think of time as a river flowing at the same rate everywhere. 1 second is 1 second everywhere for everyone. But that cannot be true if light always goes at sea. The mathematics forces you to conclude that time flows at different rates for different observers. And the key factor is velocity. The faster you move, the slower your time runs relative to someone at rest. Let me give you an analogy to make this more vivid. Imagine you are walking across a field. You can walk north, or you can walk east, or you can walk in some direction in between. The total distance you cover depends on how you divide your motion between north and east. Now, here's the key. Suppose you have a fixed walking speed. Say you walk at exactly 1 mile per hour. If you walk purely north, you cover 1 mile north in an hour. If you walk purely east, you cover 1 mile east in an hour. But if you walk northeast, you cover less than 1 mile north and less than 1 mile east, because your motion is divided between the two directions. Space and time work in a similar way. Everything in the universe is moving through space-time, and everything moves through space-time at the same total rate. We might call this the cosmic speed limit. And here is the beautiful thing. That cosmic speed limit is exactly the speed of light. If you are sitting still in space, not moving at all relative to me, then all of your motion through space-time is directed through time. You move through time at the maximum rate, 1 second per second, as it were. But if you start moving through space, some of your motion through space-time gets redirected from time into space. And that means you move through time a little slower. Your clock ticks a little slower. Time passes more slowly for you. The faster you move through space, the more of your space-time motion is going into space, and the less is going into time. Your clock slows down more and more. And here is the punchline. What happens when you move through space at the speed of light? Then all of your motion through space-time is going into space. There is nothing left over for time. Your clock stops completely. Time does not pass for you at all. This is why time stops for light. Light moves through space at the maximum possible speed. It uses up all of its motion through space-time, just traveling through space. There is nothing left for moving through time. Let me say that again, because it is so important. Everything moves through space-time at the same total rate, the speed of light. If you use all that motion for traveling through space, you have none left for traveling through time. That is what light does. That is why time stops for light. Now, let me give you another analogy to make this concrete. Suppose you are on a highway, and there is a speed limit of 100 miles per hour. You can drive north at 100 miles per hour, or east at 100 miles per hour, or at some angle in between. If you drive purely north at 100, you make no eastward progress. If you drive purely east at 100, you make no northward progress. But if you drive northeast at 100, you make some progress in both directions, but less than 100 inches each. Space and time are like north and east on this highway. Your speed through space-time is fixed at c, the speed of light. If you use all that speed traveling through space, you have no speed left for traveling through time. Time stops. Now, here is something I should be very careful about. When I say time stops for light, what do I really mean? Does light experience anything? Does a photon have a point of view? This is where we have to be honest about what we know and what we do not know. Photons are not little people. They do not have experiences in the way we do. So when I say time stops for light, I mean something very specific and physical. I mean that if you calculate what a clock would read if it could somehow travel at the speed of light, the answer is that it would not tick at all. No time would pass on that clock. We cannot actually build a clock that travels at light speed, because clocks are made of matter, and matter cannot reach the speed of light. Only massless things, like photons, can travel at c. But we can take the limit. We can ask, what happens as you go faster and faster, closer and closer to the speed of light? And the answer is that time slows down more and more, and in the limit, time stops. So when a photon is emitted from a distant star, and travels for 1 billion years to reach your eye, from the photon's point of view, there is no journey. The emission and the absorption happen at the same instant. The whole trip takes 0 time. This is one of those ideas that sounds like poetry but is actually hard physics. It falls directly out of the equations of special relativity. There is no way around it. Now, let me check myself. Let me make sure I can explain this to a bright 12-year-old. All right, young friend, here is the deal. Everything in the universe is always moving through space and time together. Think of it like having a limited budget. You have a fixed amount of motion to spend, and you can spend it on moving through space or moving through time, but not both fully at once. If you sit still, not moving through space at all, then all your motion goes into time. Time passes at the normal rate. But if you start moving through space, you are using some of your motion budget on space, so you have less left for time. Time passes slower for you. Light moves through space as fast as anything can possibly move. It uses up all of its motion budget on space. There is nothing left for time. So time does not pass for light at all. Does that make sense? Good. Now, let me address a common misconception. People sometimes think that time dilation is just about how things appear. They think, oh, it just looks like the clock is running slow, but really it is running at the normal rate. This is wrong. Time dilation is not an optical illusion. It is not about appearances. It is a real physical effect. If two twins separate, and one travels at high speed while the other stays home, when they reunite, the traveling twin will be younger, actually physically younger. Fewer heartbeats, fewer thoughts, fewer birthdays. This is real. The confusion comes because we are used to thinking of time as absolute. We think there is some universal clock ticking away in the background, and everyone's local clock is just keeping track of that universal time. But there is no universal clock. There is no background time. Time is local. Every object has its own time, determined by its own history of motion. This is hard to accept because it is so different from everyday experience. But everyday experience is limited to low speeds. We never move at speeds where time dilation is noticeable. If you fly in an airplane, time dilation is real, but it is tiny, billionths of a second. You cannot feel it, but it is there. At speeds close to light, time dilation becomes huge. At 90% of light speed, time runs at about half the rate. At 99%, time runs at about 1/7 the rate. At 99.9%, about 1/22nd, and so on. As you approach light speed, time slows to a crawl and then stops entirely. Another misconception is that there is something special about light itself that makes time stop. People think light has some magic property that freezes time, but that is not quite right either. What is special is the speed. The speed of light is the cosmic speed limit. It is the maximum speed at which anything can travel through space, and it is the total speed at which everything travels through space-time. Light travels at this speed through space because light has no mass. Anything without mass must travel at exactly this speed. It cannot go slower. If there were other massless particles, they would also travel at c, and time would also stop for them. In fact, there probably are other massless particles. Gluons, which hold quarks together, are massless. They also travel at c. Time stops for them too. And gravitational waves, ripples in space-time itself, also travel at c. In some sense, time stops for them as well. So it is not about light specifically. It is about the speed. The speed of light is special because it is the structure of space-time itself. It is built into the fabric of the universe. Now, let me take you through a thought experiment. This is the kind of thing I love to do. Let us really see how time dilation works. Imagine I have a very simple clock. It is called a light clock. Here is how it works. I have two mirrors, one above the other, separated by some distance. Let us say 1 meter. A pulse of light bounces up and down between the mirrors. Each time it completes a round trip up and back, the clock ticks once. Now, this clock is sitting still in my laboratory. The light goes straight up, hits the top mirror, comes straight down, hits the bottom mirror. Tick. The time for one tick is just the round trip distance divided by the speed of light. 2 meters divided by c. Very fast ticks, but that is fine. It is a clock. Now, suppose you put this clock on a rocket ship that zooms past me at half the speed of light. What do I see? From my point of view, the clock is moving horizontally. The light pulse goes up, but while it is going up, the clock is moving to the side. So the light does not go straight up. It goes diagonally, up and to the side. Then it comes back down, also diagonally. Here's the key. The light still travels at c. The speed of light is the same for everyone. So the light is traveling diagonally at c, but the diagonal path is longer than the straight up and down path. So it takes longer for the light to complete the round trip. You see what happened? From my point of view, watching your moving clock, the clock ticks slower. The same pulse of light takes longer to complete its journey because it has a longer path to travel. And this is not some trick of the light clock. Any clock would slow down in the same way, because all physical processes depend on the structure of space-time, and that structure says that moving clocks run slow. Now, you might ask, what about from your point of view on the rocket? From your point of view, you are sitting still and I am the one moving. So do you see my clock running slow? Yes! This is the weird part. From your point of view, you are at rest and your clock is ticking normally. But you see my clock, which is moving relative to you, running slow. Each observer sees the other's clock running slow. It seems like a contradiction, but it is not. The resolution comes when you try to compare clocks directly, and that involves acceleration, which gets complicated. But the key point is this. If you keep moving at constant speed forever, you and I will each see the other's clock running slow, and there is no paradox. The paradox only seems to arise if we try to bring the clocks together to compare directly. And when we do that, one of us has to accelerate, and that breaks the symmetry. Let me take this further. Suppose you are on a spaceship traveling at 99% of the speed of light. What is time like for you? From your point of view, everything is normal. You get up, eat breakfast, do your work, go to sleep. 8 hours of sleep feels like 8 hours of sleep. Nothing strange. Your clock ticks at the normal rate, 1 second per second. But from my point of view, watching you from Earth, your clock is running very slow. For every second on your clock, about 7 seconds pass on mine. You seem to be living in slow motion, not because of any trick, but because time itself is passing more slowly for you. Now suppose you travel for what seems like 1 year to you. You age 1 year, you have about 365 days of experience. But when you check how much time has passed on Earth, you find that 7 years have gone by. Your friends have aged 7 years while you aged 1. This is real. This is not science fiction. It is a direct consequence of the equations of special relativity, and it has been tested many times. At even higher speeds, the effect is even more dramatic. At 99.9% of light speed, time slows by a factor of about 22. Travel for 1 year of your time, and 22 years pass on Earth. At 99.99%, about 70 years pass on Earth for every year of your time. And as you approach the speed of light itself, this factor goes to infinity. At exactly light speed, infinite time passes on Earth for 0 time on your clock. Time stops for you completely. This is why time stops for light. Light travels at exactly c. The time dilation factor is infinite. 0 time passes for the light, no matter how far it travels. Now, let me show you the mathematics, just a little bit. The formula for time dilation is not complicated. It comes from the Pythagorean theorem, of all things. Remember my light clock, with the light bouncing up and down between mirrors? When the clock is at rest, the light travels straight up and down. Call that distance d. The time for 1 tick is 2d divided by c. When the clock is moving, the light travels diagonally. If the clock moves a distance L to the side while the light makes its trip, the diagonal path has length given by the Pythagorean theorem. The light goes up d and sideways L, so the total path is the square root of d squared plus L squared. Actually, that is just for one leg. For the round trip, it is twice that. But here's the thing. L depends on how long the trip takes and how fast the clock is moving. If the clock moves at speed v, then L equals v times the time for the trip. And the time for the trip is the path length divided by c. When you work this out, and it is just algebra, you get that the moving clock's tick time is the resting clock's tick time divided by the square root of 1 minus v squared over c squared. That square root is the key. When v is 0, the square root is 1, and the clocks tick at the same rate. When v is small compared to c, the square root is close to 1, and time dilation is small. But as v approaches c, v squared over c squared approaches 1, 1 minus, that approaches 0, and the square root approaches 0. The tick time goes to infinity, the clock stops. This factor, 1 over the square root of 1 minus v squared over c squared, is called gamma. Physicists use the Greek letter gamma. It is the time dilation factor. When gamma is 2, your clock runs at half speed relative to mine. When gamma is 10, 1/10 speed. When gamma is infinity, your clock stops. For light, v equals c, so v squared over c squared equals 1, and the square root is 0. Gamma is 1 over 0, which is infinite. Time stops for light. Now, some people get confused here and say, wait, you cannot divide by 0. And that is true, strictly speaking. So technically, we cannot assign a reference frame to light. We cannot say what time is like from the photon's point of view, because the mathematics breaks down at exactly v equals c. But we can take the limit. We can ask what happens as v gets closer and closer to c. And the limit is clear. Time slows more and more, without bound, approaching a full stop. That is what we mean when we say time stops for light. Let me give you another way to think about this. In relativity, there is a quantity called proper time. Proper time is the time measured by a clock that travels along with an object. It is the object's own personal time. For ordinary objects moving slower than light, proper time is real and positive. The clock ticks, time passes, but the formula for proper time has that same square root. The square root of 1 minus v squared over c squared. For objects moving at light speed, this square root is 0, proper time is 0. What this means is that light has no proper time. It does not experience duration. There is no before and after for a photon. The moment of emission and the moment of absorption, which might be separated by billions of years from our point of view, are the same moment from the photon's point of view. They are not even separated by an instant. They are identical. This is strange enough for photons traveling in a straight line. But it gets even stranger when you think about light that is bent by gravity. Light from a distant galaxy might be gravitationally lensed, bent around a massive cluster, taking a curved path to reach us. That curved path might be much longer than a straight line. From our point of view, the light takes extra time because of the longer path. But from the light's point of view, it still takes 0 time. 0 is 0, no matter how curvy the path. Now, I want to connect this back to something deeper. I said earlier that everything moves through space-time at the same total rate, which is the speed of light. Let me unpack that a bit more. In ordinary space, we measure distance with a ruler. In space-time, we measure something called the space-time interval. It combines distance in space and duration in time into a single quantity. And there is a remarkable theorem. For any object, the space-time interval along its path is directly related to its proper time. For objects at rest, the interval is purely in time. They age, but they do not move through space. For objects in motion, the interval is partly in space and partly in time. They age, but slower, because some of their interval is being used up by motion through space. For light, the interval is entirely in space. Light moves through space at c and does not age at all. Its proper time is 0. This is sometimes described by saying that we are all moving through space-time at the speed of light. If you are at rest in space, you are moving through time at maximum rate. If you start moving through space, you slow down in time, and light moves through space at maximum rate. so it has no movement through time left. This picture of a fixed budget of motion divided between space and time is a beautiful way to understand time dilation. It makes the whole thing seem almost inevitable. Of course, time slows down when you move fast. Where else would the motion come from? Now, let me mention one more thing that often confuses people. What about acceleration? When I speed up or slow down, what happens to time? The basic answer is that acceleration itself does not directly cause time dilation. What matters is your velocity. If you accelerate to high speed and then coast at constant velocity, time dilation is determined by that velocity. If you accelerate and decelerate, you have to add up all the time dilation from each moment, depending on your velocity at that moment. But acceleration per se is not the key. Velocity is. There is a related effect from general relativity, where gravity causes time dilation. Clocks run slower in strong gravitational fields. This is different from the velocity effect I have been describing. It comes from the curvature of space-time, but the two effects can work together. If you are deep in a gravity well and moving fast, both effects slow your clock. For light, gravity does interesting things. Light bends near massive objects. Its path curves, but its speed through space is still c, always c, and time still does not pass for it. No matter what gravity is doing, the photon has zero proper time. Now, let us think about what this means for our picture of the universe. Imagine you are a photon emitted from an atom in a star far away. You leave the star and head out into space. You travel for what we call billions of years. You pass through vast empty voids, skirt around galaxies, maybe get bent by a gravitational lens or two. Finally, you hit someone's retina on Earth. A human sees a point of light in the night sky. From the human's point of view, you have made an epic journey across cosmic time. Dinosaurs rose and fell while you traveled. Civilizations came and went. Billions of years of history unfolded. But from your point of view, if we can call it that, there was no journey. The emission and absorption were the same event. The star and the retina touched, in a sense. They were connected by a null interval, a path through space-time along which no proper time elapsed. The two events, separated by billions of years in our time, are adjacent in photon time. They are as close together as two events can be. This is one of the most mind-bending aspects of light. Light connects distant events in a way that makes them immediate. The light from the sun that warms your face left the sun 8 minutes ago by our clocks. But from the light's point of view, it left and arrived at the same instant. The sun and your face are, in some sense, touching. The stars you see at night, some of them no longer exist. They may have exploded or collapsed long ago. But the light reaching you now, from your point of view, has been traveling for centuries or millennia. From the light's point of view, it just left. The star and your eye are connected by an instant, a single moment with no duration. This does not mean you can send messages faster than light. It does not mean you can travel to distant stars instantly. All of that is still forbidden. From your point of view, as an observer with mass, light takes time to travel. Information takes time to propagate. Causality is preserved. But it does mean that light has a very different relationship with time than we do. Light is outside of time, in a sense. It does not experience duration. It lives in a kind of eternal present, connecting distant events without any sense of waiting or journey. Some people find this poetic, some find it disturbing, but it is what the physics tells us. It is a direct consequence of the principle that the speed of light is the same for all observers. Now, let me come back to Earth, so to speak. Why does this matter? Why should you care that time stops for light? First, it is just wonderful. It is one of those facts about nature that reveals how different the universe really is from our everyday intuitions. We think of time as a constant backdrop, ticking away at the same rate everywhere. But it is not. Time is flexible, malleable, dependent on motion and gravity. The faster you move, the slower time goes. And at the speed of light, time stops. Second, it matters practically. We have satellites in orbit carrying atomic clocks. These clocks run at slightly different rates than clocks on the ground, both because of their velocity and because of the weaker gravity up there. If we did not correct for these effects, GPS would give wrong positions. Time dilation is not just a curiosity. It is a practical reality that affects technology. Third, it changes how we think about causality and the structure of events. In our everyday experience, cause always precedes effect. First the ball is thrown, then it is caught. But relativity teaches us that the ordering of events depends on the observer. Events that are simultaneous for one observer may not be simultaneous for another. The only ordering that everyone agrees on is the ordering of events connected by light signals. Light cones, as we call them, define the structure of causality, and light itself, traveling along the edges of these cones, experiences no time at all. Fourth, it connects to deep questions about the nature of time itself. What is time? Is it a dimension like space? Is it something that flows? Why does it seem to go only one way? Relativity does not answer all these questions, but it does tell us that time is more subtle than we thought. It is entangled with space. It depends on how you move, and for light, it does not exist at all. There is a famous quote, often attributed to Einstein, that goes something like this: "The distinction between past, present, and future is only an illusion, however persistent." I do not know if Einstein said exactly that, but it captures something true. Our ordinary sense of time, flowing from past to future, is not built into the laws of physics in any fundamental way. The laws are symmetric in time, or nearly so. The flow of time is something we experience, but it is not clear that the universe experiences it the same way. For light, there is certainly no flow, no past, present, or future, just an eternal now connecting distant events in a single instant. Let me close with a thought. Next time you look up at the stars, think about the light reaching your eyes. That light has traveled for years or centuries or millennia by your clock. It has crossed unimaginable distances, but for the light itself, no time has passed. The star and your eye are connected by an instant. The universe is, in some sense, smaller than it seems. Not in space, but in photon time. Every point in the universe is right next to every other point, if you are a beam of light. This is one of the beautiful, strange truths that physics teaches us. The universe is not what it seems. Time is not what it seems. And light, the fastest thing there is, exists outside of time entirely. Now, I want to hear from you. Think about this. If time does not pass for light, does that mean the light experiences nothing, or does it mean the light experiences everything at once? I am curious what you think. Let me know your answer. Video description. What does a journey of 1 billion years feel like if it takes 0 seconds? Light leaves a distant star. By the time it reaches your eye, entire species have risen and fallen. Mountains have eroded to dust. 1 billion years have passed. But for the light itself, nothing. No time at all. The departure and arrival are the same instant. This seems impossible. How can something travel for eons and experience no time? The answer lies in one of the strangest truths Einstein ever uncovered, and it's not what most people think. In this video, we explore why time dilation reaches infinity at the speed of light, what proper time really means, and why photons exist outside of time entirely. This lecture draws on Feynman's celebrated explanations of spacetime from 6 Easy Pieces and the Feynman Lectures on Physics, particularly Volume 1. Chapters 15-17 on Special Relativity. Source: Richard Feynman. 6 Easy Pieces. 1995. Chapter 5. The Theory of Relativity. Richard Feynman, The Feynman Lectures on Physics, Volume 1, 1964, Chapters 15-17. Albert Einstein on the Electrodynamics of Moving Bodies, 1905. Credits. Written and produced by Oxido. AI-generated voice and visuals. Inspired by Richard Feynman's public lectures. Timestamps. 0, the billion-year journey that takes 0 time. 2:45. What is time, really? Clocks and processes. 7:30. The strange fact about moving clocks. 14:15. Why the speed of light is special. 21. The motion budget analogy. 28 to 45. The light clock thought experiment. 35 to 20. The mathematics of time dilation, gamma factor. 41 to 0. What does a photon experience? 47 to 30. Common misconceptions about time dilation. 52 to 15. Why this changes how we see the universe. If time stops for light, does that mean light experiences nothing or everything at once? Share your thoughts below. Warning: this video is AI generated, synthetic voice and visuals. It is an original fictional lecture inspired by Richard Feynman's teaching style and public ideas, and is not an authentic recording, endorsement, or statement by Richard Feynman or his estate. Any resemblance is for educational, creative purposes.